So for this question, we want to use the graph to find the horizontal asymptote, if any, of the function. We really need to know what a horizontal asymptote is before we look for it on the graph. Here's our definition from the notes. The line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. Symbolically, if f of x approaches b as x approaches infinity or negative infinity, then y approaches b is a horizontal asymptote. Now that wording may not have cleared everything up for us, so let's try to simplify it. When we look at this portion of the definition, it says f of x approaches b. So we want to keep in mind that f of x is y. So we're saying that our y is going to be approaching a certain number. Now in this part, it says x increases or decreases without bound. So that portion of the definition says that y is going to be unrestricted, unbounded, and unbounded is when we talk about infinity. So x is going to be approaching infinity or negative infinity. Now this x part is very significant because it tells us what portion of the graph to look at. We have our x scale, which is our x-axis here. And if x is approaching infinity or negative infinity, we're talking about this portion of the graph. This is where x is approaching infinity. And this portion of the graph where x is approaching negative infinity. So this part of the definition is telling us where to look on the graph. And if this is going to be, or if this graph is going to have a horizontal asymptote, then we need y to approach a certain number. And if y approaches that number, then we have a horizontal asymptote that number. So let me erase my markings here so that we can see the graph more clearly. And we're paying attention to what we see in blue. This line, we want to pay attention to the y value, and we notice that this graph is getting closer and closer to the x-axis. And so is this one on the other side. The graph gets closer and closer to the x-axis, and that is a y value of 0. So we do have a horizontal asymptote for this particular graph, and that horizontal asymptote is y equals 0. So on this portion, we're seeing that as x is approaching infinity, y is approaching the x-axis, which is a y value of 0. On this portion of the graph, x is approaching negative infinity, and y is approaching 0. So we do have a horizontal asymptote at y equals 0. In this question, we want to find the domain and range using the graph on the left. When I'm looking for domain and range from a graph, I like to use my ruler. And I like to hold my ruler or pencil vertically when I'm looking for domain. Because if I hold it vertically, my ruler is running across the x scale. So I want to write it in interval notation, so I'm going to go from left to right. And the first time my ruler is hitting the graph is right here. It's a little bit hard to tell, but I believe this line is continuing on forever here. So I would say that this domain starts at negative infinity and continues until we get to this vertical dashed line here. We're assuming that this line continues on forever as well. So once we get to this dashed line here, that vertical dashed line is an indication of a vertical asymptote. So it looks like this example has a vertical asymptote at x equals -3. So the vertical asymptote is an undefined spot on the graph, so the domain will start at -3. Then the graph continues right after that vertical asymptote. So the domain starts again at -3 and continues on to infinity. Now this is the domain written in interval notation, -infinity to -3, union with -3 to infinity. There's another way to write domain, and it's called set builder notation. And in set builder notation, we use curly braces. We state the name of the variable, in this case x, and then we draw this vertical line. That vertical line means such that, and what comes after the vertical line are the restrictions on that variable. So for this example, the only restriction is that x cannot equal -3. It can be any other real number besides -3. So then I'm looking for the range. I'm going to hold my ruler horizontally to find the range because my ruler would be pointing to the y scale. As I go from bottom to top, the first time I hit the graph is right here at the x-axis, and that is a y value of 0. And I'm going to put a parenthesis on that because it looks as if the graph is getting closer and closer to the x-axis without ever reaching it. And that's an indication that this graph has a horizontal asymptote right on top of the x-axis. That's a horizontal asymptote at the line y equals 0. So my range is starting at 0 and continuing on to infinity. So this would be my range in interval notation, but if I wanted to use that other notation, set builder notation, I would use curly braces. And since I'm talking about the range, that would be the y. Y would be my variable. And I want to write the conditions or the restrictions on y. And in this example, the conditions are that y needs to be greater than 0. And so that would be your range in set builder notation, your domain in set builder notation above. For the given rational function, answer parts A through C. We're given this function f of x equals x squared plus x minus 56 over x squared plus 7x. And with this rational function, we want to determine the domain. We want to determine the y-intercept, if any, and determine the x-intercepts, if any. So let's start with the domain. When we have a rational function, we have variables in the denominator. And if there is a 0 in the denominator, we have that division being undefined. Division by 0 is undefined. So that's our concern when we find the domain. We take the denominator, which is x squared plus 7x. We set that equal to 0, and we're going to solve. This can be factored. I'll factor out an x. If I factor out an x, I'll have x times x plus 7. And I can set each factor equal to 0. That gives me x equals 0 and x equals -7. These two values are going to be the restricted values. They cause the denominator to equal 0, and division by 0 is undefined. So we need to exclude these values from the domain. So we're excluding -7 and 0 from the domain, but all other real numbers will be included in the domain. So we're going to write this in interval notation. We want to represent each one of these shaded regions with a lower bound and an upper bound. So for the first one, that line goes on forever, so we use negative infinity. That shaded region stops at -7. The next shaded region starts at -7 and goes to 0. And the next shaded region starts at 0 and goes to infinity. So we have the domain of this rational function being negative infinity to -7, union with -7 to 0, union with 0 to infinity. Let's move on and talk about finding a y-intercept. You find a y-intercept by letting x equal 0. So that means I'm going to substitute a 0 into the function. Now keep in mind over here we already said that 0 is a restricted value. So we're going to see that this isn't going to work out. We have 0 squared plus 0 minus 56 over 0 squared plus 7 times 0. This gives -56 over 0. We said division by 0 is undefined, and that means that we don't have a y-intercept for this rational function. So then let's take a look at the last part, finding any x-intercepts. When you look for an x-intercept, you let y equal 0. Now we're using function notation in this example, so instead of writing y, we write f of x. So we want to set our function f of x equal to 0. We have 0 equals x squared plus x minus 56 over x squared plus 7x. To solve this, we would multiply both sides by the denominator, x squared plus 7x. And this is going to clear the fractions. So we have that denominator canceling out, and then on the left-hand side, 0 times x squared plus x is 0. So in order to find the x-intercepts, we need to solve this quadratic equation, 0 equals x squared plus x minus 56. I believe I can factor this quadratic, but if you can't factor it, you can always fall back on the quadratic formula. So x times x is x squared, and for 56, 7 times 8 is 56. I'm going to use a plus on the 8 and a minus on the 7. We can use the zero product property and set each factor equal to 0. We have x minus 7 equals 0 and x plus 8 equals 0. I'm going to add 7 to both sides to get x equals 7. Subtract 8 to get x equals -8. And we do have x-intercepts here at 7, 0 and -8, 0. You might want to check while you do this with your restricted values to make sure that the x-intercepts you came up with aren't one of those restricted values. In this case, they are not, so they are the x-intercepts for this rational function. For the given rational function, answer parts A through C. We have the function f of x equals x over x squared minus 4. We want to find the domain, the y-intercept, and the x-intercepts. So let's start off with the domain. This is a rational function, and with a rational function, we need to pay attention to the expression in the denominator. Now, the reason we focus on that is because a rational function is undefined when we have a 0 in the denominator. So we want to figure out when that denominator, x squared minus 4, equals 0, and that will give us our restricted values. So I can add 4 to both sides, and that gives x squared equals 4. I can square root both sides, and that gives x equals plus or minus 2. These are our restricted values. All other real numbers will be a part of our domain. So if we think of that on the number line, we're saying that -2 and +2 are not part of the domain, and every other real number is a part of the domain. So we can write that domain in interval notation, -infinity to -2, union with -2 to 2, union with 2 to infinity. So that gives us our domain. Then we want to find any y-intercepts. To find a y-intercept, we let x equal 0. So we're going to substitute a 0 into our function. That gives 0 over 0 squared minus 4. That's 0 over -4, which is 0. So this function does have a y-intercept, and it's at 0, 0. Then we want to find our x-intercepts. We find x-intercepts by letting y equal 0. Now we're using function notation, so f of x is y. So we're going to set f of x equals 0. So that's 0 equals x over x squared minus 4. And we want to solve this equation. We'll solve it by clearing fractions. So I'm going to multiply both sides by x squared minus 4. 0 times x squared minus 4 is 0. And on the right-hand side, x over x squared minus 4 times x squared minus 4 will cancel out that denominator and leave you with the numerator of x. So we have an equation here, 0 equals x, that is solved. X equals 0, and we get that we have an x-intercept at 0, 0 as well. So 0, 0 is an x-intercept and a y-intercept for this function. On this question, we want to find vertical asymptotes and create a rough sketch of the graph near each asymptote. We have the function f of x equals 6 over x minus 3. So to find vertical asymptotes, we first need to factor both the numerator and denominator. In this function, we have 6 in the numerator, which is already factored, and x minus 3, which is already factored. And the reason why we factor the numerator and denominator is because we want to look for the other type of break in the graph or discontinuity in the graph, and that is a hole. So the other type is a hole. And when there are common factors, that's when we have holes in the graph. So because we look at the numerator and denominator and there are no common factors, we know that we don't have any holes in the graph. And once we've established that there are no holes, we can take the denominator and set that equal to 0. And we find out that we have a discontinuity, and because that discontinuity is not a hole, we know that it is a vertical asymptote. So this graph will have a vertical asymptote at x equals 3. Now let me draw a sketch of a graph. Let me make that a little bit smaller. And at x equals 3, we draw a vertical dashed line. And the definition of a vertical asymptote is that as x approaches that value, the y will approach infinity or y will approach negative infinity. And so we need to figure out whether we're going to be drawing that graph going towards positive infinity or negative infinity. And this is on the 3 plus side. to the right of 3. And we need to figure out whether we're going to go to infinity or negative infinity on the 3 minus sign, which is less than 3. So that's what we're trying to figure out when we want to give a rough sketch of the graph. So to do that, we're going to pick a value that is a little bit more than 3 and a value that's a little bit less than 3 so we can figure out what's going on each side. So I'm going to pick something that is less than 3, which I'm going to choose 2.9. That's something that is just a little bit less than 3. And I'll pick, for something that's a little bit more than 3, I'll pick 3.1. And we're going to plug that into our function. So f of 2.9 is 6 over 2.9 minus 3. And this denominator, 2.9 minus 3, is going to be negative. And we have positive in the numerator. Positive divided by negative is a negative. So what that tells me is that on the left side, below 3, the graph will approach negative infinity. And then I'll do the same thing. I'm going to calculate f of 3.1. That's 6 over 3.1 minus 3. That's a positive value, which is 6, over 3.1 minus 3 is also positive. Positive divided by positive is positive. So on the other side, my y is going to approach infinity. So this gives us a sketch of the graph near the asymptote x equals 3. Thank you for checking out my videos. Have a great day.